To understand the relationship between a landscape, a scalar field, and the forces acting upon it, a vector, we can look at how they must balance one another to satisfy specific mathematical rules. Imagine a landscape, such as a topographical map of a mountain, where every point represents a specific value like elevation or temperature. If we introduce a force, like a steady wind, that is constant and never changes its strength or direction, the landscape must satisfy a very specific condition for their interaction to remain in balance. In this scenario, the landscape must be in a harmonic state. This means that the average value of the field around any given point must be perfectly balanced, a state known as satisfying Laplace's equation. Essentially, without any variation in the force acting upon it, the landscape itself cannot have any sources or sinks that would disrupt this equilibrium. The situation becomes far more complex when the force is no longer steady but instead varies depending on where you are, a position-dependent field. Imagine that instead of a steady wind, you now have a swirling whirlpool. When the vector field changes across space, the quiet terms in the mathematical relationship suddenly roar back to life. The landscape is no longer required to be simply harmonic. Instead, the shape of the landscape becomes deeply coupled to the movement of the force field. The way the landscape curves and slopes must now perfectly compensate for the way the force swirls, stretches, or compresses at every single point. This relationship is not just theoretical. It describes the fundamental behavior of the physical world. Magnetohydrodynamics in fluids. These rules govern how properties like heat or chemical concentrations are transported through complex fluid flows or magnetic fields. Stretching and shearing. In a visual simulation, you can see this coupling in action. A simple pulse of heat placed in a whirlpool vector field will be stretched and sheared by the flow. A balancing act. The mathematical identity acts as a balancing condition. It ensures that the spatial changes in the flow's direction and the spatial changes in the landscape's height are in perfect sync. By visualizing these interactions, we can see that the local geometry of a field and its global transport behavior are inseparable.